Is that too loud or is it all right? Okay.
All right, so we're going to get started. So thank you, Young Ray, for accepting an invite in an hour or so of me sending an email saying I happen to be in Canada.
I said I'm on the way to Waterloo in a couple hours, so I'll be right in.
Yeah, he has a BMath and a CSBE. I assume that is electrical and electronics.
Electrical engineering electives. It's called.
From 1987. Ex-Microsoft DevTools architect, FPGA soft processor enthusiast, and he'll share a brief retrospective on his wonder years in Waterloo in the 70s and 80s, present a sampler on his more software-friendly approach to reconfigurable computing, talk about FPGA overlay architectures like the GRVI Phalanx Kilo 4 RISC-V processor array connected with an NoC, the Hoplite NoC, which you heard about, and a design space exploration of a non-trivial application, and some comments on how you might want to do research and think about, planning your career.
Yes, that's a lot. All right. Welcome, everybody. Thank you very much, Nachiket. It's wonderful to be back here at my alma mater. So here's the outline of my talk. I'm going to talk a bit about computing here in the late 70s and early 80s for a few minutes. Then I'm going to go back to about 2014 and show some slides that show the origin of an on-chip interconnect network optimized for FPGAs called Hoplite, why it exists and what its features are. I understand you'll be talking about that later in your course. And then an application of that where I build a 1,000-core system on a chip that sits on top of that Hoplite NoC, the design of that system. I'll then talk about some not implemented ideas that I have for taking Hoplite forward. One's a design space exploration of how to do a certain gadget, which I'll explain. And the other is on cache coherence on this system. And I know that cache coherence is also going to be part of your program in this course. And then I'll end with some free career advice for what it's worth. So my family moved here in 1976 when I was 12. And I spent 5 years on campus as a teenage twerp and then 5 years as an undergrad. And so I'm going to talk a bit about what computing was like here back then for a few minutes. So when we moved from Toronto to Waterloo, I was the saddest kid you've ever seen. Toronto was this wonderland with the Science Center and Children's Village, the subway you could explore. And we were free-range kids, so we just had the most incredible experience in Toronto, whereas Waterloo then and now is not quite as exciting as Toronto. So I basically moped in my room for a year after we moved out here. But when I was 13, a neighbor who was a professor in the physics department brought me into the university, gave me a tour of the physics building, masers, thin films, cryogenics, astronomy stuff, and they had a little computer lab. And I said, could we please go back to that computer lab? In that lab, they had a Data General Nova 1200. It had 8K of core memory, and it ran time-shared BASIC. And the classroom had 6 terminals and a little sign saying, to get an account, type this. So I made myself an account, and now I could read and write my programs, and I could access some games that people had created, and I was just in heaven. So many days after school, I would go into the university and I'd be on this system. I found that there was a certain door in the back of the physics building that didn't quite close properly, so I could get in there in evenings and on weekends. And that was a wonderful year. There were very few computers in the entire city, right? So all Waterloo High School students had to share one computer in one high school. I never even saw this computer. So our computing environment at high school was, you had a couple of key punches in the back of a classroom. You could key punch your Fortran programs, or you could get optical mark cards and in pencil, type in your Fortran statements in pencil. You take your deck, you put it in a box, a courier would take it to the other high school, some student there would run all the jobs from your high school, you get a printout back 2 days later. So 2-day turnaround. That's not like IDEs and on-chip, online debugging and stuff. So it actually taught you a really good algorithmic mindset of executing code and data in your head to make sure that it was always going to work the first time, because it was so disappointing when you had like a syntax error or a mistype and you had to do another 2-day wait for your stuff to come back. So being able to come to the University of Waterloo as a high school student and more or less borrow the resources there was quite wonderful. But then someone said, the real action in computer science is over in the math and computer building, that beautiful brutalist fortress. And I quickly found the Math Society, and these wonderful undergrads and grad students were very kind to this little 14-year-old twerp and took me under their wing and really treated me well. And if you've seen the film Almost Famous, that was also my experience here in this amazing place of glamorous undergrads. Now, I found that mathematics was powered by bridge, coffee and donuts, Dungeons and Dragons, that kind of stuff. But the computing environment back then, for most students, was in the so-called Red Room that used to be on the first floor in the center of the MC building. And they had a couple of IBM 370 mainframes, and then arrays of tape drives, which were always spinning with these vacuum column things, really cool. And then DASDs, which IBM called them, which were just big washing machine-sized hard disks. And the student computing environment was up on the second floor. You can see the windows up there. You could be key punching stuff into a deck that you put into a card reader. You would read through the card reader, and then a moment later, your output would go out of these line printers, which were super loud and super fast. Or the students would be on terminals like this, the 3270s, using time-shared IBM stuff called VMCMS. This was also the era where we started to see the introduction of 8-bit micros. So my first computer was a TI-59 programmable calculator with a little card reader that would run through with your programs. A friend had a KIN 1, which had a 6502 and 1K of memory. And then in March of '78, Byte Magazine came out with reviews of the new Commodore PET and the new Apple II. The TRS-80 had just come out. So we just got this kind of commodity 8-bit microcomputing. And that was an era where everyone could type basic programs in, save them to a cassette, and magazines had all kinds of program listings. You'd buy magazines to take programs and type them into your computer, save them to a cassette, and so on. That was the computing environment. Now, that was an expensive machine. I don't know if it was $2,000 in '78. So I would go down to the Eaton store in downtown Kitchener, and on the first floor, they had a Commodore PET on display in their calculator department, and I did my computing there in the Eaton's department store. Back at the university, across the hall from the Math Society office was the Computer Science Club office, which was a student chapter of the ACM. So this was where the really cool elite computer science undergrads would hang out. Nowadays, they win ACM programming contests and all this kind of stuff. The main computer that we were using was owned by the Math Faculty Computing Facility, or MFCF, called the BUN, which was a Honeywell 6660, which is an interesting 36-bit architecture machine. We used terminals in a terminal room, and we wrote programs in B. Now, B is the precursor to C. It's got all the C keywords, but no types. So everything is a 36-bit word. And you can also pack six 6-bit EBCDIC characters in it, or 4 9-bit characters. So when you did character-oriented operations, you had to call functions to pull characters out of the words. When you did a plus, that did an integer add. When you did a hash plus, that did a floating point add. So no types. And so this, in fact, was some code I wrote in 1980 to pay for my computer time back on the BUN for that semester. Things got really lovely. Also that, in the late 70s, but I discovered in 1980 that up on the 6th floor, there was a PDP-1145, which is a 16-bit architecture, and it had maybe 256K of semiconductor RAM by this point, and it was running Unix version 6, or a special Waterloo version of Unix. And of course, it was programmed in C. So that's the actual machine on the left. There's a little sign on it which says "Caution, expensive stuff." And on the right, that was our terminal room. We had 6 or 8 of these Volker Craig 24 by 80 serial port character terminals. That guy's name is Charles Forsyth, and he was one of about 8 super elite Unix hackers. Waterloo got Unix before almost anyone in Canada and was a hotbed of Unix research in the late 70s and 80s. And we also had, in the Computer Science Club office, ACM distinguished lectures. So we had everybody at Bell Labs if you look at the old Unix papers, they all came through Waterloo. Mike Lesk, S.C. Johnson, Rob Pike, Brian Kernighan, all these guys came and gave us lectures about new stuff in Unix. Okay, in fact, in the electrical engineering department, you also had two PDP-11s in Johnny Wong's Computer Communications Network group. And one of those two machines is in my garage in Bellevue, Washington. I got that machine on its way through recycling, and I'm gonna restore it. It's still sleeping right now in my garage. Okay, so around 82, another thing that Waterloo was known for, I mentioned those IBM mainframes. This guy Wes Graham, Paul Dirksen, and Don Cowan created something called Watt4 and Watt5, which were these great Fortran environments for teaching, and they were used all over the world and were world famous. By this point, they said, let's try and recreate that success in the microcomputer era and try and allow students to learn APL and Pascal and Fortran and 6809 assembly and stuff. So they built this platform called the SuperPET, where they did a deal with Commodore where they took the Commodore PET microcomputer and they added another board into the machine with a 6809 and some DRAM and some EPROMs, non-volatile memory. And it ran all these languages. And they decided to employ local high school students to help with this. So I had 2 summer internships working on Waterloo Micro APL. And APL, by the way, is a gorgeous functional language you need to check out at some point. Along the way, I still didn't have my own computer. And I really wanted one. So and I couldn't afford one. So my computer science club friend said, just build your own. It's not so hard to take the chips. We'll show you everything you need to do to get a working computer. And I built up a computer from scratch. I learned to wire wrap using that. Oh, sorry. Oh, yeah, that's right. Up here, this gadget here is a wire wrap tool. You stick wire into the tip and you twist it around a post, and that leaves a wire on that post on the bottom of an IC socket. You can then connect that wire to another IC socket and wrap it around that post. So I learned to wire wrap IC sockets and boards. I built a 6809 system. It had video, it could talk. And this taught me to read IC data sheets and app notes. And that's a really great skill if you haven't gotten into the habit of it, is to go and read the manufacturer's data sheets and app notes to really understand what the thing can do. And ever since then, I've been comfortable working in both hardware and software. And I think that's kind of a superpower for a computer engineering student to say, I want to show you that this can work, so I'll go build the hardware to do it. Or I want to show off my hardware. I guess I need to go and hack something in the Unix or the Linux kernel to light up my new hardware innovation. So I encourage you to be comfortable working in both of those. And of course, you can then do co-optimization of your design, which is now called hardware-software co-design. So I won't bore you with my undergrad experience, but I did get this interesting BMath honors co-op CS triple E degree. This program had terrible attrition. This was the first year of CS students that took EE courses. Only about 1/3 of the people in this program actually got that degree. Most of them dropped down to a CS degree or something else. And there's a complementary degree called EECSE for the electrical engineering students to take more CS courses over in the math department. That also had bad attrition. So I assume your engineering and computer engineering, electrical engineering, computer engineering program has no such attrition now. I will say that it was a fantastic time, and we all got an incredible diversity of computing experiences on all kinds of different hardware, different machine architectures, different operating systems, and different languages. And I wonder if today's undergrads get any of, and grad students get any of the same richness and breadth of very different ideas, instead of just Unix, Python, C++, Rust, or whatever. Anyway, along the way, I had wonderful professors and TAs and grad students and distinguished lecturers, really mind-opening. And we did some great course projects that all ended up being used, in my experience, in my career later. When I had the grad school or industry decision, I followed a buddy who had gone to Microsoft the previous year. That was an incredible, lucky choice. And I had a wonderful career at Microsoft doing software developer tools. So I wrote C++ compilers and .NET, C# platforms and distributed systems and stuff. But all of the Waterloo experience and I hated moving here to Waterloo, but it turned out to be my luckiest thing that happened in my life. Now, I mentioned we had some great professors, and I wanted to bring up an EE professor that we had, T.R. Viswanathan, who taught all kinds of places and also worked in industry. And he would be giving a lecture on MOSFET biasing or something, and then he'd just stop and he'd give us a little anecdote or a joke or a bit of career advice. So a kind of joke you'd hear from him is he'd say the best capacitors are silver mica capacitors because the mica comes from India and the silver comes from Flin Flon here in Canada. But some advice he gave me that really stuck with me and really resonated was he said, after university, you might go into industry, and how you do in a big company, he described by the VIP rule. He said, your career is proportional to visibility times image times performance. As a good EE professor, he said, performance leads image like voltage leads current in an inductor. Over time, if you do a good job, your image will improve, but it doesn't matter if you don't have visibility. If your boss's boss, who makes the promotion decisions, the compensation decisions, doesn't know about you and your good work. And then he said, conversely, if you're doing a bad job, low visibility is a good thing. Okay, enough. I'll just conclude by saying I was a super lucky kid, and I never take for granted what a wonderful child and teenage years that I had. And also, I got to live from the dawn to the dusk of Moore's Law. My computing experience had 1 MIPS 8-bit micros, many core PCs and GPUs, serial terminals at 110 baud, networking at 100 gigabits per second, memory factors of millions and billions, and memory bandwidth of factors of millions of improvements. No one in the history of history has ever lived in an era where your experience got 1 billion times better in one lifetime. And it'll never happen again, I'm afraid to say. So that's all over, and more on that later. Okay, enough about reminiscing. So I'm now going to talk about your syllabus and about on-chip interconnect networks, and revisit some early days of a NOC that I think that Nachiket and I have worked on and that you'll be looking at later in the course. And I gave a keynote in 2014, which is looking at the past of FPGA soft processors. Those are microprocessor cores implemented in the FPGA, looking at the past of that in the 90s when we could barely fit one onto a chip, and then looking forward to what's the future going to be like with these things. And in the middle of that talk, I said, how many of these simple 1995 era RISC processors could we put in a modern FPGA? So I picked this device, the Vertex 7690, which has about 400,000 6-input lookup tables and about 1,500 block RAMs, which are 4K memories. And I said, how many 300 LUT processors could I put on there, and what kind of a overall system parallel computer architecture would you build with that? So I'm actually going to walk you through the kinds of things I think about when I'm designing a soft processor that might be useful to you down the road. So I want to build this very simple RISC processor. I'm going to be using Xilinx 6 LUTs. I'm going to be using on-chip memory. It's going to be a chip multiprocessor with shared memory across the cores. I needed instruction set architectures. I'll just take Xilinx's Microblaze RISC processor, which is a nice simple one, and build a subset of that. In this design, it's going to have small instruction kernels, so maybe 4 or 8K of memory is going to be all there is for the instruction that we're running, new instructions. In any kind of RISC processor, these are the essential things. You have to be able to fetch instructions from an instruction memory. You need a register file, an ALU, a program counter, some logic for branching and conditional execution. And you need to be able to load and store words from memory. All the rest, that's the stuff you absolutely have to spend hardware on. All the rest you can maybe do in software or make it configurable. So byte and half word load and store I made optional. If you provide a multiplier that you share amongst a bunch of processors, then you don't need shift instructions because you can accomplish shifts with multiplies. And then you think about the pipeline design. you want to focus on the most critical path. Like I want to be able to have pipelined add instructions, add, that run at 1 per cycle. That we've got to get right. And the critical path there is that you've got the operands for the add. We'll call them the A and B operand registers. They go through an ALU. Then you go through a MUX to select the ALU as one of the possible results of that instruction. And then you put it through another MUX called the register file forwarding MUX, which you use in a pipeline processor. Hopefully you've encountered some pipeline processor design, and then back into the operand registers. So that's a recurrence. The data starts in operand registers and might end up back there. That is about 3 or 4 LUT delays, and it should run at around 3 nanoseconds. The rest of the processor should be organized so that you can still get a 3 nanosecond cycle time or a 300 megahertz processor. As we're using block RAMs for instructions and data, and they're synchronous, any accesses to those memories, you'll present an address, wait for the clock to rise, and then you get your data out. So there's going to be a clock cycle boundary there anytime you go to those memories. And in a classic 5-stage RISC, there's actually more stages than you need to have a reasonably pipelined machine. So I typically delete the memory stage and make load instructions take like 1 more cycle. In exchange for that, you simplify a lot of the microarchitecture and you save a lot of gates. Now, as I said, it's going to be a multiprocessor, and we're going to cluster and cluster the processors to try and share resources. The block RAMs have 2 ports. You can simultaneously do reads and writes on 2 ports into each of these 4K block RAM memories. So we're going to use 1 block RAM and share it amongst 2 processors for instructions and another one for data. And we're going to share a multiplier made out of DSPs. And if you then start to do some physical design, you go into your FPGA design tools and you open up an empty FPGA and you look at where are all the sites where the block RAMs are and where are the sites where the LUTs are. In these devices, you found that for every 2 block RAMs, you have about 160 slices, and in this era, there were 4 lookup tables per slice. So you get about 640 LUTs of total budget for all of your system for each 2 block RAMs. So what does one processing element get? It gets about half of that, and then maybe 3/4 of that, because you want to have some leftover for other stuff. So maybe our budget for one processor is 240 LUTs. Can we make it fit? So if you look at what that very, very austere data path might be, it's got a register file. Registers go through operand muxes. One of the ports has register file bypass and the other one doesn't. It's got operand registers A and B that feed an ALU. There's a next PC thing that handles branches that takes the program counter and these registers. There's a data out register for store instructions, and there's an instruction register. Pretty elemental. And so the next thing you have to do is say, how do I map that into my physical FPGA 6-input lookup tables? You have to know this stuff to do good co-design. And so for the register file, it turns out with 4 LUTs, you can get a 6-bit, 1 write, 1 read synchronous RAM. So if you have 2 copies of that and you make enough columns of that, you can get a 32 entry 32-bit register file that has 1 write port and 2 read ports. The 2-to-1 muxes here, if you realize that the 6-input lookup tables can be fractured into 2 5-input lookup tables, you can form 2 bits of a 2-to-1 multiplexer in each LUT. And so for every 4 LUTs, you get 8 bits, and you also have 2 sets of those for the A and B operand muxes. Using some carry logic tricks that Xilinx has, you can build an ALU that has only 1 LUT delay that does both add and subtract and does logical operations. Similarly, the next PC. And the result mux is just a simple 4-to-1 mux, which you can implement in a 6 LUT with 1 LUT per bit. So with that kind of thinking, you then say, how does this get laid out optimally on the physical chip? And so this represents a very carefully floor planned implementation of that data path, where on the left, the orange and red stuff, that's the register file. The light orange and lime green stuff is the operand muxes, the A and B muxes. The green column is the ALU. The blue column there is the result mux, etc. And the purple stuff is the program. It's only a 16-bit program counter because we don't have much instruction memory. So you have a small program counter and branch logic. And then in the right, these two salmon-colored things are the instruction and data RAM for this processor and another one. So you then take two processing elements and you have them share one data block RAM and one instruction block RAM, and you add some multiplexers to access them by both processors and by the network. And you then take two copies of that, and now any of the four processors can do a load or a store that is going to get sent into the network, or a result from the, maybe I can use a pointer here. I won't bother. The result from the network can be written into either of these block RAMs. And there's another data path there that handles the case that some remote agent did a load out of your memory, and the load response needs to re-enter the network to deliver the load response to the remote cluster. So now we get to the on-chip interconnect network. So we've done 4-to-1 concentration. So we have these four processors that are sharing one network input and one network output. How are we going to connect this all up on our system on a chip? Now, a popular way to do this is to build a 2D torus network. And typically this requires a 5-port router, which talks for any given node in the network. It talks to the north, south, east, and west neighbors in a bidirectional way. And it's got a connection, as we showed down in the bottom here, it's got a connection to your local cluster that can take messages that are ingressing into the network or can deliver messages out of the network. And if you do the math for our modern FPGA with 4 processing element clusters, we're going to need 250 of these routers. And then you go to the excellent Interconnection Networks textbook, and you say, how do I design a 5-port router? You'll need at least a 5x5 crossbar. You'll use virtual channels. You'll need buffering. I'm sorry, let's show what the textbook says. You'll need buffering. You'll need switch allocation logic and arbitration. You'll need FIFOs. It's an enormous piece of hardware. It's larger than our 4-processor cluster, so it's not going to fit. So what do? You can't do that. So you need something super austere, and I thought, what's the most austere router that's possible that can take some bits from here and teleport them over there? It simplifies a number of those bits of router dogma to build a really, really stripped down gadget. So it uses unidirectional links. So data only flows on a given X ring or Y ring. It only flows in one direction. And any router is on some X ring and some Y ring. The entire message enters or leaves the network in one go. You don't chop it up into packets and send it 32 bits at a time. If you need a 300-bit message, you give it 300 bits in one go. There's no buffering, but the network will not accept a message until there's at least an output, a local output port for it. It never drops messages, but they can bounce around for a long time. And it uses something called dimension-ordered routing. So the message first traverses on an X ring to the right X coordinate, and then it traverses down a Y ring to the destination XY router where it leaves the network and is handed to the cluster. Now, it might be the case that a message is coming in from the north and a message is coming in from the west, and they both want to go south. What do you do? In this extremely austere design, the north to south message has priority, and it is delivered north to south. And since the west message has nowhere to go, it deflects east, which isn't where it wanted to go. It's like you wanted to make a right-hand turn, but you can't. So you're forced to keep going straight. You have to drive all the way around the city again to try and turn right. the next time. So you deflect all the way around this X ring. That's fine if it doesn't happen very often. So this is what I call base hoplite. And as you see, the guts of the router are just two 2-to-1 multiplexers. Although it looks like it's got 5 ports, it's actually got 3 inputs, north, west, and in, and really only 2 outputs, south and east. The output to the client is the same link as the southbound output. And that's very beneficial in an FPGA. So that was the idea. Now, if you then use that austere router and you tile the whole chip with these 4 PE cluster data paths, we can get 1,000 PEs on this device. I call that initial architecture Phalanx. It means something. That's what I called it in 2014. I've kind of changed what I mean now. But it did reflect this very ordered, regular 2D array. But what about latency and memory systems and stuff? So as I mentioned, these RISC processors could take 1 cycle to do loads and stores to their local DRAM, their local SRAM. But if they want to access some other processor's memory, it's going to be 10 or 12 cycles away, or it's going to be 25 cycles away, or it's going to be 35 cycles away. Best case. And if there's deflection, you can add some more tens to that latency. So what kind of workloads might make sense in this kind of strange machine? Only things where the data is resident in these SRAMs, and ideally where it's very local accesses by the processors. And it's out of the question to add like DRAM to this, because you'd have 1,000 processors fighting over a couple of 10 or 20 gigabyte per second DRAM channels. It wouldn't make sense. We really needed a better kind of FPGA with more DRAM bandwidth, which did come. So a couple of takeaways from this early work. There's a notion that I like of hardware software co-design of, I was going to do this complicated, expensive thing in hardware, but I don't need it every cycle. I only use it once in a while. Maybe I can do that in software instead and take all that hardware out of the system. And now I have more resources. I could put more processors down or more routers. Another is the value of really understanding the physical design and technology mapping so that when you make architectural decisions, it reflects a good physical design. So you could easily build a 32-bit RISC that uses 2,000 LUTs instead of 200 LUTs if you're not thinking about how does this decision impact which LUTs I'm going to put down in the design. And the way to get that kind of insight is, unfortunately, to sit there in the Xilinx tools and push design little test circuits through them and see what comes out and try and get those insights about what circuit tricks can I use to make this a factor of 2 smaller, remove a LUT delay or 2 LUT delays from a critical path, etc. There's no substitute for iteration, and I still do lots of iteration learning new chips. It's also beautiful and liberating to be working with tight constraints and budgets. We looked at the textbook router design. It was so huge that I didn't have to think about it anymore. It's just too big. I can't use it, right? So it's nice to know what you're giving up, but then by all means, you have, especially in an FPGA, you have license to give it up and build something that's cheap and cheesy and lightweight. So in this case, I was just focusing on the essential. All I wanted to do was teleport bits from A to B, and in that particular workload, Hoplite was the right answer. And so I like to say simple is beautiful. Simple architectures are easier to design, easier to optimize, easier to get right. They're smaller and faster. Okay, a couple more things on Hoplite before I move on to an application of it. I typically think of the router this way. There's 3 inputs, the Y input, the X input, and the I input from the client, and 2 outputs, X and Y. There's usually some logic in implementations of this router that look at address information on the message. What's the destination XY address? Are we doing multicasting? Are the inputs valid or not on this clock cycle? Sometimes the router will have 0 valid inputs. Sometimes it will have 3 valid inputs. The router is a little bit of logic which decides what's going out, a little hardwired arbiter which decides what's going out on the X and Y ports. Are they valid in this cycle for the downstream router? It also asserts the control signals that handle flow control about accepting input messages from the client core. Then there's a switch, and the switch is the thing that's actually moving the very wide message, 70 bits on 300 bits, from YI, XI, and I to these output ports. And it turns out you can build this fantastic 1 LUT per bit of routed data circuit trick where you take a 6 LUT, you split it into 5 LUTs with 5 inputs, and it can compute with the select 0 and 1 up to 4 transfer functions of which inputs go to what outputs. And if you pick the transfer functions correctly, you can get a lot of stuff, including dimension order routing and multicast and some other things that are in the paper that Nachiket and I have in FPL 17 that maybe you'll read. And this system typically uses dimension order routing, which says if YI is valid, it's going out in Y. Otherwise, if XI is valid and it wants to go out on X, it'll go out on X or Y, unless it's busy. And only then do we consider accepting input from the client. So this is what some routes look on this. In the upper left, you sent a message to yourself in red. And then at the 1, 0 to the right of that, we injected it at 1, 0. It went to 2, 0, and went to 3, 0, and then left the network. Then at 0, 1, we set one down the Y ring to 0, 2. Or from 1, 1, we were trying to send to 2, 3, so it went to 2, 1, so it gets the right X coordinate, and then turns south and goes to 2, 2 and 2, 3, and then leaves the network. And then at the bottom, the 1, 3 node was trying to send a message to 2, 0. And it wanted to get to 2, 3 and turn south, which then goes around the ring. But at that moment, that output link was busy by the red thing. So it has to deflect and go all the way around. And 4 more cycles later, it then gets onto the right Y ring and gets delivered up at the top. With this same data path, you can also do Y dimension multicast. So the node at 0, 0 can send a message which goes to all of the clients on that Y ring. It takes 3 cycles to do it. And the guy at 1, 1 can send a message to some other Y ring. So it goes to the X equals 2 Y ring and then goes and gets delivered to all of those nodes. Similarly, you can manage to do X multicast. Whether in the green case here, it's very simple. You send it in at 0, 2 and it goes to 1, 2, 2, 2, 3, 2. Or in the more tricky case up at 0, 0, where you're trying to send to everybody on the Y equals 1 ring. So you have to go to each of the Y equals 0 nodes to then forward those messages down to that ring down there. And you can also get deflection when you're doing these multicasts. And you can combine these features and get XY multicast, so you can do a broadcast of a message to everything in the network. And I don't think these are esoteric. I think these are essential features of a NoC. There's lots of workloads where you want to replicate or broadcast results to a lot of other agents, and you want to do it more efficiently than sending each of them a message. You just want to say, hey, everybody, this is really important. I've used this in a number of different ways. Now, I mentioned that that Hoplite has this, that base Hoplite has this deflection behavior, which is if I can't get onto the Y ring right now, my messages are going to go all the way around that X ring again. This becomes pathological at relatively low injection rates, which is another thing I'm sure you'll study. So this base design has a glass jaw that as you put more and more traffic into the network at the same time, it quickly starts bogging down, where if you were just a little smarter about it, or if you just had a little buffering here or there, you could handle the fact that at this moment, 2 messages want to go south instead of deflecting the message around an X ring. And so this was, and in the, I think we have this data in one of our papers, another version of this data in one of our papers, where we say, if the average delivery time is 5 or 6 or 7, that's not bad. But if you push the injection rate up, you quickly get a terrible situation where it's taking 200 cycles to deliver your message. And Nachiket and his students have done some very nice research on ways to fix this in all kinds of different dimensions. I'm going to skip this one. So overall, this Hoplite idea is much, much less expensive than the textbook router, which after all was optimized for ASICs. So there was a refereed paper on something called CMU Connect, which built a 32-bit router with 2 virtual channels. And that thing used 1,500 lookup tables for one router. And it took 3 cycles to route messages. And the latency, the pipeline critical path was about 10 nanoseconds. The comparable 32-bit router built with Hoplite, depending on addressing, is under 50 LUTs. It takes 1 cycle to go through a router, and it does it in 3 nanoseconds. So overall, it's 100 times better area times delay, which is amazing, but it's very apples to oranges. As I mentioned, we have this pathological behavior on deflection and so on, but it's so cheap that you can build multiple Hoplite NoCs and other things. As I mentioned here, after this initial work, Nachiket and his students have explored all kinds of nice applications and improvements to this. I'll mention that multicast is free. I don't know if there's any multicast in your syllabus, but I think it's definitely interesting to think about. And of course, in the aftermath of this, there have been, not aftermath, parallel to this, there have been a number of companies that have added hardened physical networks on chip in their FPGAs. First in the Acronic Speedster, then in Xilinx Versal, and then in some Altera HBM FPGAs. They actually build a NoC built right into the hard logic of the thing. Turns out soft NoCs still have a role even in these FPGAs with hard NoCs, but I won't have any content on that. How are we doing? I'm getting through my hour. Okay, next I'm going to talk about an application of this to build kind of the 5 years later version of that other multiprocessor that you saw me talking about, which is called GRVI Phalanx, which is a 1,000-core, 64-bit RISC multiprocessor on one Xilinx FPGA, and it has this wonderful high bandwidth memory. Do you know what high bandwidth memory is? Okay, cool. So the genesis of this also dovetails into Andrew Putnam's talk. When we were doing Catapult, and we had built that decision tree scoring engine that got us a 100x speed up over software that you heard Andrew talk about, I went to bed at night worried that Microsoft Research would come up with a better Bing ranking accelerator algorithm that would obsolete all of our hard-earned Verilog-based custom-built decision tree scoring accelerator. It was also an incredible chore to take the rest of that software stack and get it well integrated with the FPGA accelerator. That was actually way more work than getting the accelerator gadget working. And this is a problem with, in general, FPGA-based compute accelerators. It's really hard to take a living, evolving software workload, map it to that spatial fabric, and then keep it working because your software guys want to try new algorithmic ideas and stuff. It's also even hard just to get engineers that can work in FPGA accelerators. There's 100 performance software engineers for every FPGA computer architecture engineer. Doesn't scale up well. So I thought, can we use these FPGAs as accelerators, but make it more familiar to programmers? And the idea is to give them basically lots and lots of general purpose processors as well as their custom accelerators. So they could run parallel C++ or OpenCL kernels across hundreds of soft processors, but still add custom function units, custom memories, custom data paths, custom interconnects. And if you use this approach, more of their design iterations are 5-second recompiles rather than a 5-hour place and wrap job for the FPGA. So that's kind of where I was trying to go with this. And that led to this non-product of mine called the GRVI Phalanx Accelerator Framework. And it's basically an evolution of that thing you saw from 2014. It's a processor cluster array overlay. So you have very austere processing elements, which you then compose together into clusters, and you then compose those clusters into the overall SoC. They all sit on a NoC, and they all access the various resources of the SoC through the NoC. And just as before, but now in the RISC-V instruction set architecture, my philosophy is that if you build simple PEs, you can get more of them on a chip and enjoy greater parallelism, especially memory parallelism. So back in 2015, I designed an austere 32-bit RISC-V, and then you can then pack 8 of those into a small tile, which has 4K or 8K instruction memories, which is still too small. It has a much larger shared data memory, 128 kilobytes. It's organized as a 4-way address bank interleaved thing, so you can do 4 loads or stores to it each clock cycle. It's still got some free ports, so you can add memory-based accelerators that could pull up to 256 bits per clock cycle in and out of those memories. And that uses just 3,500 LUTs. So in a 1,000,000 LUT FPGA, you can have quite a few of these tiles. Then to compose it together, I went back to Hoplite, which, as we mentioned, uses single flit messages, unidirectional rings, deflection routing, and multicast. Here, instead of like 70-bit messages in the previous design, I went to 300-bit messages, which was enough to carry a 256-bit data payload, which is 32 bytes, plus a 40-bit address, plus multicast data, and that kind of stuff. And even on a mid-sized FPGA of this era, it only uses a few % of the die for the routers, because the routers are only using 1 LUT per bit of link width. So when you add in green the router stuff to this cluster, you have a Hoplite router. The outputs from the router can be written into the cluster memory. The inputs to the router can be read out of the cluster memory. So you have a design where you can send or receive 32 bytes per clock cycle per tile times all the tiles in the device. Now, addressing on the whole chip is called PGAS, or Partitioned Global Address Space. And an address might have the multicast control bits, X and Y addresses, and a local 20-bit address, or it could be a 40-bit DRAM address out to DRAM. And when you tile 50 copies of that in a mid-sized Kintex UltraScale 40, that's 400 processors. And when you tile 210 copies of it on a larger FPGA, a Vertex UltraScale 9 Plus, that's a 1700 PE design. Altogether in those cluster memories, there's a total of 26 megabytes of SRAM. And the peak not to exceed performance of this in aggregate is about 400,000 million instructions per second if the whole thing runs at 250. And that uses about 40 watts. And so down here I have like a 1 processor RISC-V system, a 32-core GRVI Phalanx, and a little proto board, and then this big design. And I guess we've seen some of these statistics. One of the figures of merit for a NoC is the bisection bandwidth. If you saw it in half at the worst place, what's the maximum amount of traffic that you can carry? And in this design, it was 900 gigabits per second. Each processing element only used about 25 milliwatts, which was good because we had so many of. Oh, and the design took 11 hours to go through the tools. So like that 2-day turnaround story, you really want that job to finish successfully each time. So it had a lot of shortcomings. It only had it was a 32-bit processor with 32-bit pointers, so it was a pain to build these 40-bit addresses. And when I wanted to run this on some big Amazon F1 FPGAs in the cloud, they can have up to 1.5 terabytes of DRAM that you might access. So you really do want bigger addresses. And because it's only doing 32-bit word accesses, it's wasting half of the bandwidth on the ultra RAM block RAMs that are that cluster memory. Because the processor is so simple, it has an in-order microarchitecture. So when it does a load, and the load has to go through that interconnect to the cluster memory and then back to the processor, that takes 5 clock cycles. The processor stops for 5 clock cycles waiting for that load. That all sucks. The biggest problem, though, is it's again useless to have 1,000 processors and a couple of DRAM channels. It's just not enough memory bandwidth. So it really had to wait for a better kind of FPGA, which did arrive. So in 2019, we got the UltraScale Plus HBM2 FPGAs from Xilinx. This is physically what it looks like. There's 3 FPGA logic dies, and at the bottom there's 2 stacks of DRAM. Each of them has 4 gigabytes of DRAM. Each of them is basically 8 128-bit DDR4 DIMMs, but in a little tiny stack. So altogether, the way this is exposed to the FPGA designer is at the bottom of the chip, you can kind of see these purple stripes. Each of those is a 256-bit wide port that you can clock at 450 megahertz, and there's 32 of them. So if you can keep them all busy every cycle, you can read or write up to 460 gigabytes per second. And now that you're starting to get enough bandwidth to make it interesting to put processors up above that. So it was necessary to redesign GRVI Phalanx for HBM FPGAs. I wanted latency tolerance so the processor could do other stuff while it was doing these loads. I wanted to widen everything to 64 bits. And I wanted to somehow light up those AXI HBM ports at the bottom to get all that memory bandwidth. So, and another thing, to get all the bandwidth from the processors down to the bottom of the die, I doubled the number of NoC columns from the earlier designs so you could carry more traffic down and up. In redesigning the processor, a really simple way to make a processor more latency tolerant without adding a lot of out of order issue junk is just to put a register file scoreboard on the register files. So if you launch an instruction that's going to take a few clocks and it's going to write to register X5, you mark X5 as busy. You remember, oh, X5, I haven't got the result back yet. And then when you then issue later instructions in the pipeline, if they access X5, that instruction has to stall, waiting for X5 to finish. And then in software, you can schedule the long latency operations so that the thing that defines the value is a few cycles away from the thing that uses the value, and then you never actually wait for it. So I have an example here where I'm doing a block copy of 8 64-bit words from the from array to the to array. And if you schedule it that way, on the right, you can see kind of a pipeline trace of that running. In red, that's indicating that, for example, the instruction that's loading a value into T3 hasn't come back yet. And on the next cycle, T1 hasn't come back either. And on the next cycle, A7 hasn't come back. And at the worst point, we have like 7 loads in flight. But because we don't use those load results till a bit later, it doesn't cause the pipeline to stall. And so this whole block copy of, I guess, 64 bytes takes 20 clock cycles, which is a great improvement over the previous design. Altogether, widening the processor to 64 bits and adding this latency tolerance let us kind of double the bandwidth of computation from the processors into that shared memory. That's a key figure of merit for this kind of architecture, the compute and memory bandwidth into your SRAM. So then that was just one cluster, one of these little green boxes. You could, on this particular chip, put over 200 of them in I used a 15 by 15 NoC. At the bottom of the NoC, there are these bridges which bridge NoC traffic and the Xilinx hardened AXI HBM2 bridges. So I needed to somehow take messages on the NoC that were meant to be memory accesses and perform the memory accesses on behalf of some cluster somewhere else. And so for each A, we have 2 of these H bridges, so it can do reads and writes on 2 separate dedicated channels. And then at the bottom of the die are these 2 HBM stacks with the 32 memory channels. So to perform a memory access is quite a process on this design. You have to, in the cluster, format a remote DMA read or a burst read or write request that you then send down the Y ring to one of these bridges, which queues it. And then when the Xilinx bridge is ready to accept it, it hands it to the Xilinx bridge to work on. So there's a lot of queuing and pipelining in the design. As you may know, DRAM accesses are really slow, like hundreds of clock cycles. So in fact, you need to have a lot of traffic in flight to max out the bandwidth of the thing. So I had queues in my cores, and Xilinx has queues in their cores. The thing didn't timing close at 450 the way I wanted. I could only get it to timing close at 300. And with the NoC that I designed, I was only getting 130 gigabytes per second write bandwidth peak across the whole thing, plus 130 gigabytes per second read bandwidth happening all at the same time. So that's less than half of the max bandwidth of the device. Sir.
Sorry, quick question. So you said you could also do a DMA operation. Does that mean
That's what basically, to do any kind of memory access in the DRAM, software has to send a message to this I call it the RDMA bridge. And the message says, please write these 32 bytes here, or the message says, please read some burst of up to 512 bytes. And when you have that read, stream it back up the NoC and write it into my cluster memory at this address. So it was a model where you copy big buffers of data from your cluster SRAM as kind of a staging area down to this RDMA bridge, which was queuing them, which then drained them into the HBM. Or you could, the read path was better because you could send a big burst read. These HBM channels also don't like doing small operations. You do not want to store a byte or even a 64-bit word. It's a total waste of the bandwidth. And in fact, 32-byte transactions are also not ideal. You really want to send really big operations to max out the little protocol that they're running in their, basically it's many, many, many copies of a DDR4 DRAM all in this stack. Does that answer your question?
And so just to be clear,
Yeah.
the Hoplite packet is still a flip, right? You're not creating a stream of
Well, in fact, the response comes back as a bunch of 32-byte read response transactions. Each is completely separate. Because they're on a Y ring, and because I'm controlling the traffic that's on the Y ring, there's nothing in between. Like any traffic that is going to the bottom is going to get absorbed in the write channel or read request channel FIFOs. I didn't have good flow control on flooding that. So that was a part of the design that I never finished. What happens if every cluster on this column suddenly decides to do a massive amount of memory traffic? It would overrun the FIFOs. So I really needed very limited credit flow control there, but I never finished the design, frankly. Yes, sir.
So you mentioned that if there's a stream going on, and also in the previous design you mentioned that if there's like south, essentially like east and north,
Yes.
want to go to south. So if like there's a long stream coming in, it's gonna get cut off.
No, so one of the reasons that this is all happening on the Y rings is because I need to bring things from a vertical dimension in the chip down to this one place. But the beauty of using the Y ring for this traffic is that traffic that's accepted into the Y ring never deflects because the Y ring traffic has priority. So once a cluster's memory access request is accepted by the ring, it will be delivered in a known number of clock cycles to its destination on that ring with no deflection, and happens in order. So if you put, one of the other problems with deflection is it breaks out of order delivery. So if you have some protocol built on the NoC that says I must say A, B, and C, and A deflects and B doesn't deflect, the poor receiver gets B, A, C out of order delivery. That can break some protocols. In this case here, all of the DRAM traffic is contrived to only use Y ring channels. So there's no deflection in delivery of those messages, and they all happen in order. Thank goodness. I'm going to skip ahead here. So one of the great things about using an FPGA to figure out things like HBM, even if you're going to use them in an ASIC, when you use an FPGA, you can use tools like the integrated in-circuit logic analyzer cores. So you can have your HBM design and attach debugging in-circuit logic analyzers into your design, and then inspect that with your PC so it can collect traces. So this is a trace I collected at some point in 2019 of one of these RDMA bridges and its transactions with two AXI HBMs. And in both of them, I was able to set up the ILAs so I could see some of the transactions in flight. The takeaway here is, although the stuff, you can see one set of signals wiggling, inside the stateful Xilinx bridges, they have a whole lot of requests that they're working on, scheduling, ordering to then deliver into the HBM ports. So from this work in 2019, I cranked out two different designs, one with 8 of the 2015 GRVIs per cluster and one with 6 of the 2019 64-bit thing. So it's still, both had over 1,000 cores. So this was the first kilocore RISC-V SoC in the world, the first RISC-V with HBM in the world, and anyway, in 2019, the highest bandwidth RISC-V system in the world. And the fact that a single engineer can do that in a summer reflects the power of the Xilinx platform and the democratization of technologies that FPGAs can afford, which is actually my first point. One of the things that I came away really excited to investigate from this work was what I called computational HBM, but it's now called processing near memory, which is, hey, instead of bringing all the data from the DRAMs up to some processor to do some boring thing with it and then sending it all the way back down and burning all of that energy and burning all of that NOC resource, for certain kinds of computations, just do them right at the HBM memory controller. So that's things like doing scatter, gather, loads, and stores, perform an add to memory, block 0, block copy, hash this block, do some selection and reduction on the data, regular expression sort. And a really important one now in AI is having sparse data structures that you let the memory controller walk for you instead of bringing back to the processor cache hierarchy, blah, blah, blah. Pointer chasing and index chasing happens more and more in some of these AI kernels. Please do that either in the memory itself or next to the memory in the memory controller. Yes, sir.
Sorry, one follow-up question. What if the HBM die was stacked on top and not at the bottom, like it is here, right? I think this problem is because the HBM is all the way at the bottom.
If it was a 3D stack.
Yeah, then this knob could just access things, whatever, right?
Well, it's interesting. The way that HBM is physically made, all of these, I said there's 32 memory channels altogether, 16 pseudo channels per stack. They are isolated vaults of bits. If you come in on controller 0, you can only access controller 0's bits, not the one that's right next door in the same stack. And so Xilinx had to add a gadget in their AXI HBM bridges, which provided a limited knock horizontally. So if you came in on AXI controller 0, and you're trying to access memory over here, it would move it horizontally for you. And I mention that because even if you have a 3D array of memories on your spatial fabric, what happens when, for whatever reason, you want to access some memory over there? And so there's actually a wonderful workshop at Supercomputing on memory. I forgot the MEMSys. I can't remember what the damn thing was called. But there's very interesting work on what do we do in the memory system so that more of the memory you're accessing is in the same vault as the computing that wants to access it. Yeah. What do we do in algorithms and blocking of these big tensors we're multiplying to try and keep things physically near certain physical memory controllers? That's going to be super important. A sad coda to this work. I love this chip, my favorite FPGA ever, this VU37P. It's dead. So there's been so much money being spent on super expensive NVIDIA and AMD GPUs and other AI accelerators that all want the latest and greatest HBM3, HBM3E, that the memory suppliers, SK Hynix and or Samsung, whoever that was, stopped providing or told Xilinx, bad news, we can't make you the HBM2s we promised. And so both Intel Altera and AMD Xilinx suddenly end-of-lifed these fantastic devices. Ordinarily, an FPGA family is sold for 30 years. But this one went from being born in 2019 to being killed in 2024 because of the economics of AI using high bandwidth memory. And Xilinx has a new device called the Versal HBM, which uses HBM2E, and I wonder if it's also doomed, that they're going to say, HBM2E memory, nobody wants that. They want HBM4, so good luck. So it's wonderful being able to use HBM devices in FPGAs, but they're really at the bottom of the food chain for them. Okay, I'm almost done. More recently, I've been working on something else, which is called the RISC-V Composable Custom Extensions Test. I won't talk about that today. It's very interesting work. But I have had some more GRVI Phalanx ideas. These are not implemented, but I wanted to bring them both up because they also resonate with some of your coursework. So we don't build these, like that GRVI Phalanx thing, I never did anything useful with it other than to say, I made a 1,000 core machine, blah, blah, blah. I never had a really compelling workload for it, although I had lots of ideas. And in 2019, I was challenged to say, what's an interesting application? And the one I want to talk about today, that's an important real-world application, is running NVMe, which is you have these little NVMe SSDs in your laptops, and that's the software contract. That's how disk IOs are done today through this NVMe protocol. And in a data center running a guest OS on a hypervisor, that's how it issues disk IOs. And I want to build a gadget that lets you have a data center guest OS issue disk IOs to NVMe, and then it gets put over the wire over TCP/IP using a protocol called NVMe over Fabrics over TCP. And what happens to the OS? The OS, to do a disk IOs, it submits them using what are called IO queue pairs, which is a data structure in the host server's memory. It has, for each channel, for each kind of logical disk, it has a submission queue, which has a series of 64-byte command packets. And a command packet like number 5 might be, please write that 4K over there at that DRAM address to that block on that disk over there. That might be the command packet. And eventually that gets processed by the NVMe disk, which reads the memory from the host, writes it onto the disk, and then sends a completion queue entry to the host saying, I did command 5, it's done. So that's the protocol that's used, and the OS thinks it's talking to a real disk. But in this scenario, there isn't a real disk on the controller, rather it's connected to a network. So as I mentioned here, the NVMe drive uses DMAs to read host memory to get the submission queue entry, to get the command. It performs the disk IOs, which may involve DMAing memory buffers out of the host or into the host, and then updates the command keys. And as I mentioned, it pretends to do this. This is, by the way, what I assume that Andrew's Azure Boost is doing exactly this kind of workload. They're accelerating remoted NVMe accesses on behalf of guest OSs. So the question was, can we do this using GRVI Phalanx? And this is a bit of an eye chart, but these are all the moving pieces that I think are involved in doing this. You have the x86 host, which has a bunch of threads. It's running some toolkits that let you use NVMe for I/O. In its DRAM, you have submission queues and completion queues, including I/O, submission queue 1, and completion queue 1. It's pointing at buffers that are going to have to be written or read from by the NVMe device. then that's on the host side. Then there's a PCI Express card, which is going to have your accelerator on it. It uses a PCI Express bridge. That's connected to the rest of the system by the Hoplite NoC at the bottom. There's a NoC AXI bridge, which is not unlike the one I just described in the GRVI Phalanx. Then you have a number of clusters. One is the admin cluster. It's got like 8 RISC-V processors, and it's running the NVMe protocol with the host. And when the host puts a command record, a submission queue entry into one of these queues, the host does a programmed I/O to a PCI Express bar register, which is like a memory mapped register. The host writes a word there. It's called ringing the doorbell. It says, hey, I've deposited a command on I/O queue number 1, go do it. And that wakes up a processor in one of the I/O clusters, of which there are many I/O clusters, to go and read the command, interpret the command, and do the command. And then there's also a TCP/IP stack that has to be implemented. And up in the upper right there's a CMAC, which is a 100 gigabit per second SerDes for connecting to 100 gig Ethernet. And there's also, just like in the GRVI Phalanx, there's a memory controller on another bridge. I won't go through all this, but it's many, many steps for the host to write a command into its submission queue to please do a 4K write, which then wakes up something over here, which then schedules an event in the next thing, which then does a DMA from the host to read the command, interpret the command. Oh, it's a write. I've got to read 4K. It sends another 4K read back to the host, reads all that memory. It encapsulates it in NVMeoF frames that are encapsulated in TCP frames that are encapsulated in IP datagrams that are then sent over the NoC and into the CMAC and then out to the partner. And then when response comes back, you have to take those messages, decapsulate them from TCP/IP, look at the response that came from the root drive, like I did the write or I didn't, and then deliver a command, completion queue entry back to the host saying it's done one way or the other. That illustrates that all kinds of stuff is going to be traveling over this Hoplite NoC among very different agents. Some are bridges to different things, some are processor clusters, some are network interfaces, and so on. There's a whole lot of data flow to this, a lot of places where I go to sleep, and then in response to something happening, I wake up and do a computation, and then I go to sleep again. All of that, just looking at this problem, gave me a lot of insight into what Hoplite sucks at and so on. But to sustain 100 gigabit data flows through this and max out those links that you have to max out, you need to have several 100 gigabit feeds continually flowing with no deflection or slowdown. So for writes, you've got to be DMAing 12 gigabytes per second from the host, and you've got to be sending it to the TCP port. For reads, you've got to take the read responses from that at 100 gigabits and deliver them into the host. If you're dealing with TCP retry, where packets got lost, you might have to buffer the packets you're sending out, so you have to send them to local DRAM and then read them back, etc. So you need to somehow design that NoC, not only for good random traffic, but no matter what happens, all of this traffic will flow. And that you can do that with even a simple interconnect like Hoplite, but you need to have dedicated columns, dedicated rings for things, so there's no contention on those. I found it a very interesting exercise. Okay, one last one in this stuff, which is, I'm so excited for you guys. I love cache coherence. I love this book. This is your book, right? This is the best textbook I've ever seen. I've read this front to back twice, and I dip into it all the time. The people that wrote this are a genius. And I'll mention that one thing you'll learn, I don't think you've gotten to this point yet, but one thing you'll learn is everybody talks about, oh, there's a state machine on every cache line, the MSI state machine. It's invalid, or it's shared, or it's modified. And the state machine is like this one in the bottom left. As you read the book, you realize that that's the ideal state machine with those green nodes. But in fact, everything you do takes time. Processor 1 does a read, and that causes events that cause messages to go over the NOC to the other processor caches. And then you have to wait for their acknowledges to come back. They might be in different states. And so you get all these transient states in blue. And then if you want to do something innovative with your cache protocol, as they show here in this lovely set of slides from you, Nish, it gets even crazier. You'll see this. Don't worry, don't fret. You'll get it. But I just love this stuff. It's just so interesting. And the cats really capture the gestalt of it. So I was thinking about GRVI Phalanx sucks for programming. I can't run Linux on it. I can't run any kind of reasonable code on it. The memory system with these clusters, which is very hardware efficient, is unlovable and unusable. It's time to bite the bullet and make this thing a cache coherent system. I would redesign the clusters so that maybe have 2 PEs and local data caches implemented in UltraRAM. And there'd be a last level cache in front of the memory channels that would be in slices, a distributed, sharded kind of last level cache, and some kind of interconnect. Great, I know how to do all that. And I've looked at how I would physically floor plan the tiles with what processors go where, and this VRAM holds instruction cache data. Those VRAMs would hold data cache tags for the data cache data that's in URAMs. I know how I do the textbook stuff about directories. I think, are you going directories in your?
Yeah. So the last lab for the graduate students is to build this, but not this physics.
Yeah.
They're going to build a cache coherence layer on top of Hoplite.
Excellent. So one of the problems with cache coherence is what other cores, data caches, are sharing my line? And you're tracking, oh, Nachiket's got it and Jan's got it. So if Nachiket wants to upgrade to being able to write it, then he's got to invalidate me. And so there's somewhere in the system, there's some hardware that's tracking who's sharing this line. Well, that doesn't work if there are 720 data caches. You just can't build a hardware gadget that tracks 700 sharers, and then when I need to invalidate you, waits for 700 acts. So the protocols that you're going to be studying in your textbook, which are fantastic, don't scale to this kind of crazy ass system. So you reject the heterodox approach. At this scale, we can't do what you're going to learn in your class. It's something called single writer, multiple reader abstraction. You can't track all that stuff. So maybe this is more for Nachiket's benefit. What I want to do is provide sequential consistency, but only for data race-free programs. That is discussed in the book. And so I want to focus on programs where there are regions where we're sharing memory, and the sharing happens in a lock or under a mutex. I'm sure you've encountered those concepts. And only focus on the synchronization variables. They're the ones that trigger special behavior. And in response to entering a lock, it's correct and simple to just flush your iCache. And in response to leaving a locked region, it's correct, if not optimal, to write back all of your dirty data. And the book talks about this a little bit, and there's a very, very nice paper that for some reason didn't get into a conference called NEAT, which is more frugal than Mezi, and it uses lots of cleverness to not do flushing all the time. It still doesn't scale to my kind of scale, but I have some more ideas on that. So I'm excited to eventually build hundreds of cores kind of cache coherent system, even though that's madness. Okay. Last 2 slides. Free career advice. Is this okay?
Yeah, go ahead.
Yeah. So I encourage you all to join ACM and IEEE and use them as your way of keeping current throughout your career. You're going to get a job. Maybe you're going to go into academia. Maybe you're going to industry. Out in industry, stay in these organizations, subscribe to the particular publications, engage in what they're doing, maybe go to some conferences, at least look at the conference papers to keep current. It's so easy to get obsolete in your 35 or 40. Don't do that. It's also fantastically interesting stuff. Study, as I mentioned back in 1980 land, study data sheets, app notes, and tech standards as they emerge. I learned so much reading the NVMe spec and then the NVMe over Fabric spec. And it was really interesting stuff. And because you have FPGAs in your toolkit, try some of these things. There's actually usually app notes and pre-built demos that let you use that 100 gigabit Ethernet or let you use that PCI Express bridge. If you try this, then in your job, PCI Express is no mystery. You can build a gadget that lives on PCI Express. You're the engineer that can do that thing, which is great. And similarly, try and work up and down the stack. Don't get stuck at one layer. Understand what you're doing and how it fits into the big picture of ultimately your company's product or your industry's standard. That really helps you find optimizations that otherwise are invisible. In thinking about where you go work, I'll just point out that in my experience, big companies pay well. They teach you how to build products and ship them to millions of people, sometimes at planetary scale. They build cred in your resume. I don't know if Jan's any good, but at least he worked at Microsoft, so he couldn't be terrible. And they can take your ideas and your dreams to market. And there's nothing as sweet as having something you want to enable in the industry and having a way of bringing it out. A big company typically has the elbows to get things to market that are good. Don't forget to take care of yourself and your health. I wrecked my health at like 28, and don't overwork yourself. Budget time for staying well, eating well, getting lots of sleep, all that stuff you hear, but it's really important. When you're in industry and your head's down working on something, these things can go away. Don't forget. I know lots of people at Microsoft who got divorced because they were so focused on their work that they let the family life go away. This is ultimately your ticket to career longevity and happiness. You're all responsible. You're all the enablers of the next generations of technology. So you got to really think through how what you choose to work on is getting put out into industry and what people are going to do with it, what bad people might do with your work. Okay? You see, I can name a bunch of companies, I won't, that are doing evil things, and the evil things are not done because the CEO wants to do them. It's because some engineers are happy to take the money and do the evil thing. Don't do that. Be able to look at yourself in the mirror at the end of your career and say, I made the world a better place, not a hellhole. And then finally, in terms of a research agenda for all of you, energy efficiency is everything forevermore. It's the only thing you're going to be working on in your whole career. You might not realize it yet, but that's it. So on the left, last slide, promise is the last slide. On the left is the NVL4. It's the latest hotness, and literally the latest hotness in AI. It's got 4 GPUs and 2 multi-core parts. That one board, 5,400 watts. And they're expected to build racks of them, 72 high with liquid cooling, and then many, many banks of these racks. A single rack is 380,000 watts, okay? We can't keep scaling up we can't say next year we're going to do, 400, 500, 600,000 watts in one rack. We can't make these things work. So Denard scaling is over. Moore's law is basically over. To get the next 10x, the industry is always excited not about 30%x, but how do we get the next 10 times improvement? You're going to have to take what you're doing now and do it in less than 10% of the current energy. And so that is going to mean you're going to work on new algorithms, co-design, integration, specialization, processing and memory, packaging, and all that stuff. There's so much waste in the whole hardware-software stack that it's full employment for all of you. What used to be fun is going to be, in your experience, a real slog to squeeze 3% out of this and 5% out of that, but all of those are worth it. Thank you very much. It's not going to be I don't know where you want. Okay, outside. Thank you, guys.